Hello everyone. In last lecture of the differential equation, we revised some basic concept that we studied already in FY basic class. So given a simple differential equation of first order and first degree, then how to solve it? First of all, we check whether it is in variable separable form. If so, then we separate the variable, integrate on both sides and solve it. If not, then we go for whether it is a homogeneous differential equation. If it is homogeneous differential equation, then it must be of the form dy by dx is equal to f of xy by g of xy, where f and g are homogeneous function of the same degree. In that case, we put y is equal to vx, differentiate on both sides, replace dy by dx by v plus x into dv by dx and solve this differential equation. If it is not homogeneous differential equation, then we check whether it is a non-homogeneous differential equation of the type dy by dx is equal to a1x plus b1y plus c1 divided by a2x plus b2y plus c2. We try to reduce this non-homogeneous differential equation to homogeneous differential equation by using the substitution, and again by using the substitution y is equal to v into x, we solve this differential equation, this non-homogeneous differential equation. Next one, suppose given differential equation is not in variable separable form, it is neither homogeneous nor non-homogeneous of the standard form, then how to solve it? Then we go for the next method. We try to find whether it is a exact differential equation. When differential equation of the type m dx plus n dy is equal to 0, where this capital M and capital N are functions of x and y. Okay, x and y are independent variables. So in that, this differential equation is said to be exact if it satisfies the condition dabba m by dabba y is equal to dabba n by dabba x. We already studied all these things. So if so, then directly we try to find the solution. Its solution is given by integration of m dx keeping y constant plus terms in n independent of x into dx into dy, okay, plus constant of integration is equal to 0. So this is the formula to solve exact differential equation. If it is not exact differential equation, then we try to find integrating factor. So what is the integrating factor? So if given differential equation, that is m dx plus n dy equal to 0 is not exact, then we try to make it exact by multiplying by some function, say I of xy, which is a function of x and y, and after multiplying by that function, this becomes exact. Okay, we try to find this suitable function, and that function is called integrating factor. Now how to find this integrating factor? There are several rules, and in the last lecture we discussed all that rules. Okay, also one more special kind of differential equation is a linear differential equation of first order and first degree. It has a standard form, that is dy by dx plus p of x into y is equal to q of x. If differential equation is of this type, then directly its integrating factor, we may write in short as if, is equal to e raised to integration p of x dx. So we try to find this integrating factor, okay, and then solution is given by y into if is equal to, in the integration symbol, this q of x, which is on the RHS, into if into dx plus constant of integration. So in this way, we can solve this linear differential equation of first order and first degree. But suppose differential equation is of higher order, but its degree is still 1. Then how can we define such type of differential equation and how to solve such a differential equation? So that's the thing we are going to focus in this lecture. So first of all, we introduce what is the higher order linear differential equation. Linear means its degree should be 1. Okay. So what do you mean by degree again? Once again we revise. Try to find highest order derivative in the differential equation and see its power. Its power is 1, then we say that degree of the differential equation is 1. Okay. So now this is a differential equation. Now if RHS of the differential equation is non-zero, that is this over here it is R of x. If R of x is non-zero, then we say that this differential equation is non-homogeneous. If R of x is equal to 0, then it will be homogeneous. Now next thing is, now here B0, B1, Bn minus 1 and Bn. Suppose they are functions of x. Suppose they are functions of x. Okay, here y is dependent variable and x is independent variable. So all this b0, b1, bn minus 1, bn are functions of x, and r of x is not equal to 0, and also observe its order is n. This is highest order derivative term in the differential equation. So its order is n and degree is 1. So it is called standard linear differential equation of the non-homogeneous form. If r of x is equal to 0, then same equation becomes homogeneous linear differential equation. Okay. Now, suppose this b0, b1, bn minus 1 and bn are the constant independent of x. Then this equation becomes b0 dny by dxn plus b1 dn minus 1 y by dxn minus 1 plus so on plus bn minus 1 dy by dx plus bn y is equal to 0. Now this is a linear differential equation of nth order. Also it is homogeneous because RHS is 0, as well as here all the coefficients are constant. So it is homogeneous linear differential equation with constant coefficient. So in this topic we focus on this such type of differential equation, homogeneous differential equation with constant coefficient. Now next thing. Now this is a differential equation. Suppose y1 is some solution of this differential equation. So obviously it will satisfy. We may replace here y by y1. Similarly, if y2 is also solution, then we may also replace y by y1, y2, and equation gets satisfied. Okay. So if y1 and y2 are solution, then what can you say about c1 y1 plus c2 y2, where c1 and c2 are constant? Yes, we have to prove the result. Then in that case, C1y1 plus C2y2 is also solution. So how many solutions are possible for this differential equation whose order is n? How many at most solutions are possible? See, linear differential equation, that is dy by dx plus p of x into y is equal to q of x, which is of first order and first degree. We have just single solution. Y is given by or y into if, or I'll shift if on that side. So y is equal to 1 upon if in the integration symbol q of x into if into dx plus c. Okay, is the solution. C upon if. I have shifted this if, which was already in the on the LHS. I have shifted over here on the RHS. So it is a general solution of the linear differential equation of first order and first solution. So we have single solution because order is 1. Okay. Similarly, suppose we have second order differential equation. So take a simple example. Suppose d2y by dx square minus y is equal to 0. Okay. How many solutions are possible? Suppose if I choose, say, y is equal to sin x, then second order derivative of sin x, first order derivative y prime is nothing but cos of x and y double prime is minus sin x. So call this as equation 1. So if I substitute in equation 1 y double prime, so is nothing but d2y by dx square is minus sin x minus sin x, sorry, over here I'll make over here plus. So plus y is nothing but sin x and that gives us 0 which is nothing but RHS. So y is equal to sin x is solution of this differential equation 1. So we try to find if there exists one more solution or not. So take y is equal to now cos x. So y prime is equal to derivative of cos is minus sin x and y double dash is equal to derivative of sin is cos. So minus cos x. So substitute in equation 1. Second order derivative is nothing but y double prime and that is equal to minus cos x plus y is cos x and that is equal to 0 and that is nothing but RHS. So both are the solutions of this differential equation. So call this as y1 is equal to sin x and y2 is equal to cos x. So y1 and y2 are the solutions of this differential equation. So or if order of differential equation is 2, then there are two solutions. So in general, as we result, if order of the differential equation is n, then there are at most n distinct solutions. Okay. Now, next thing is if y1 and y2 are solution of this differential equation, then c1 into y1 plus c2 into y2 is also solution. Okay, instead of proving the theorem, we prove for this example. So, how to check? So, C1y1 plus C2y2 is also solution. So, what is C1 into sin x plus C2 into sin x is solution. So, I'll call this solution, say, with we have to check actually whether it is a solution. So, I will call this one as linear combination as y. Okay. So, what is y prime? Now, minus C1 cos x plus C2 cos x. Y double prime is nothing but minus C1 sin x minus C2 sin x. So, if I replace in LHS, so LHS of 1 is nothing but here second order derivative of y is nothing but y double prime. So, that is nothing but minus C1 sin x minus C2 sin x plus y. What is y? Y is C1 sin x plus C2 sin x. And obviously that is equal to 0. So if y1 and y2 are the solutions of this differential equation, then obviously C1 y1 plus C2 y2 is also solution of the same differential equation. Now next thing is that suppose these are the solution. Suppose the linear differential equation is of nth order and nth degree. Sorry, first degree. Then how many maximum number of solutions are possible? Obviously, n solutions are possible. So, I will call that solution as y1, y2 and so on yn. So, are the maximum number of solutions. So, its linear combination is c1y1 plus c2y2 plus so on plus cnyn. So it's a linear combination of these solutions and obviously just now we proved for the example this y is equal to this linear combination is also solution of differential equation 1. So thus if y1, y2 and up to yn are the solution, then their linear combination of all solution is again solution of the differential equation. Okay, and this type of solution is called general solution. Okay, so it is a general solution for homogeneous linear differential equation. But if differential equation is not homogeneous, in that case, is it possible? No. So we'll discuss it separately. Now next thing is, what is a Wroskian? So now we know that there are at most n linear there are n solutions for linear differential equation of nth order. Now are all solutions are linearly independent? So we just revise some concept of linear algebra over here. So given a solution, say y1, y2 up to yn. So when these solutions are linearly independent, so just we revise the definition from linear algebra. Okay. Suppose y1, y2 up to yn are solutions of nth order linear differential equation given by just now given by equation 1. Okay, so now how should be this solution? All these solutions should be n minus 1 times differentiable. That is the must condition. Okay, and this y1, y2 up to yn are n minus 1 times differentiable functions of x. Okay, one more thing, let c1, c2 up to cn are constants. Are constant. Then first of all we defined Wroskian, and from that one we defined the definition of linearly independent. Okay, our basic definition of linearly independent is that C1 y1 plus C2 y2 plus so on plus Cn yn is equal to 0. If it is equal to 0, that always implies all the constants are equal to 0. Then we say that this all y1, y2 up to yn are linearly independent solutions. Now if one of the Ci is non-zero, in that case we say that all these solutions are linearly dependent. Okay. Any example? We take a simple example. Suppose we'll take suppose y is equal to 4 and y is equal to 5. Are these solutions are linearly independent? Y is equal to 4 and y is equal to 5. Can it be solution of the second order differential equation? And if so, are they linearly independent? So first of all, to check linearly dependence, I'll consider linear combination of these two solutions. So 4 into C1 plus 5 into C2 is equal to 0. So what I am getting here, if, okay, here 4 is non-zero, 5 is also non-zero. Okay, and this linear combination equal to 0. Okay, when it is possible, if 4C1 is equal to minus 5C2 or C1 is equal to minus 5 by 4C2. So therefore C1 depends upon C2. C1 is equal to minus 5 by 4 times C2. So C1 depends upon C2. So therefore this C1 and C2 are dependent. Okay, and they are non-zero. Okay, if can it be both equal to 0? So if both C1 and C2 are equal to 0, then this is 0 and this is 0. Then that is the unique case. But if one of the C1 and C2, either C1 or C2 is non-zero, then yes, then in that case C1 is equal to minus 5 by 4 times some non-zero number C2. Okay, so there exists some scalars which are non-zero and such that this linear combination equal to 0, then we say that yes, these two solutions are linearly dependent. Now any example of linearly independent solution? Take a previous example. Suppose y is equal to sin x and y is equal to cos x. Are they linearly independent? We'll check it. So take linear combination c1 into sin x plus c2 into cos x is equal to 0. Okay. Now we have to check for any value of x whether c1 and c2 both are equal to 0 or not. So take x is equal to 0. So it gives us sine of 0 is 0, cos 0 is 1. So therefore c1 into 0 plus C2 into 1 is equal to 0. So that gives us C2 is equal to 0 and put C2 equal to 0 again in the same equation over here. So I'll get C1 equal to 0. Okay, because here sine 0 is 0. So here C1 should be 0. Then only whole term will be 0. Now take x is equal to pi by 2. So what happens? Sin pi by 2 is 1 and cos pi by 2 is 0. So that is equal to 0. So that gives us C1 equal to 0. Okay, C1 plus 0 equal to 0. So C1 equal to 0. Put C1 equal to 0 over here. So that obviously gives us C2 equal to 0 for any x. Not for particular, for any x. Okay, then C2 equal to 0. So thus C1 and C2 should both be 0. Okay, for this solution. So therefore this C1 sin x and cos x are linearly independent solution. Now what is a Wroskian? So we defined again what is a Wroskian. If y1, y2 up to yn are solutions of nth order linearly differential equation and y1, y2 up to yn are n minus 1 times differentiable functions of x, okay, and c1, c2 up to cn are constant, then Wroskian is given by, it is denoted by w and is given by determinant of order n. So what is that determinant? 1, y1, y1, y2 up to yn, y1 prime, y2 prime up to yn prime and so on. Y1 n minus 1 derivative, y2 its n minus 1 derivative and yn its n minus 1 derivative. So this determinant is called Wroskian. Now if this determinant equal to 0, then we say that this y1 up to yn are linearly dependent. If it is non-zero, then we say that these solutions are linearly independent. So we use this is a simpler method to determine whether the given set of solution is linearly dependent or not. So take simple example. Given a solution y is equal to y1 is equal to 1, y2 is equal to x and y3 is equal to x square. So are these solutions are linearly independent? So we consider again in the same way linear combination and we work out in the same way. But instead of that one we use over here Wroskian. So what will be Wroskian? Wroskian by definition is nothing but y1, y2 and y3, y1 prime, y2 prime, y3 prime and y1 double prime, y2 double prime, y3 double prime. So we try to find it. So y1, y2, y3 are 1, x, x square. y1 prime is 0, y2 prime is 1, y3 prime is 2x, y1 double prime is 0, y2 double prime is 0, y3 double prime is 2. Okay. So directly its determinant is 2, which is not equal to 0. So therefore, this given set of solution is linearly independent. Now instead of this one, if I choose the example y1 is equal to sin x and y2 is equal to sin of x plus say pi by 2. So now here take one more, y3 is equal to sin of x plus pi. So again Wroskian is given by this determinant. Now we put here y1, y2, y3. y1 is sin x, y2 is sin of x plus pi by 2 and y3 is sin of x plus pi. Its derivative of sin is cos x. Over here it is cos of x plus pi by 2 and cos of x plus pi. Then next one minus sin of x minus sin of x plus pi by 2 and minus sin of x plus pi. Now if I shift this minus sign outside, okay, then minus of, over here I'll get sin x, sin of x plus pi by 2 and sin of x plus pi. On the next row, cos x, cos of x plus pi by 2, cos of x plus pi. And last one, sin x, sin of x plus pi by 2 and sin of x plus pi. Now observe this determinant. Here first and last rows are identical. So if any two rows or any two columns are identical, then directly its determinant is equal to 0. 0 with minus sign is again 0. So that's why here Wroskian equal to 0. Hence these three solutions are linearly dependent. So you can work out using the same technique whether the given set of solution are linearly independent or not.